Hello everyone, I am Dr. Himamaheswara Rao, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Welcome to the course Introduction to Atomic and Molecular Spectroscopy. Here we discuss different topics: introduction, principles of spectroscopy, interaction of radiation with matter, spectrum of electromagnetic radiation, interaction mechanism, various spectroscopic techniques, applications of spectroscopy, and references. Introduction. Atomic and molecular spectroscopy is a branch of analytical chemistry and physics that deals with the study of interaction of electromagnetic radiation with matter. This field plays a crucial role in understanding the structure, behavior, and interaction of atoms and molecules, offering insights into the wide range of scientific and technological applications. The techniques employed in atomic and molecular spectroscopy provide valuable information about energy levels, electronic configuration, chemical composition of substances. By analyzing unique spectral fingerprints of different elements and compounds, scientists can identify unknown substances, elucidate reaction mechanisms, and explore the fundamental principles governing energy and matter. It continues to provide new fascinating possibilities for deeper understanding of the building blocks of matter. The term spectroscopy defines large number of techniques to measure radiation to obtain information about the structure and properties of matter. The basic principle common in all spectroscopic techniques is to shine light on the substance and observe how the light is responding to such a stimulus. For example, it may be a powder sample or solid, or it can be any liquid taken in a cuvette or any transparent glass material. So whenever light incident on such type of materials, we observe the light reflected or transmitted through these type of materials. In the coming slides, we discuss all those things in detail. So for example, at the starting stage of atomic spectroscopy, when a white light or sunlight is incident on a glass prism like this, it disperses light according to their wavelengths. Here we can see different colors at different ranges on the screen. When we arrange the screen here in this region, like violet, indigo, blue, green, VIBGYOR colors. All VIBGYOR colors are observed on the screen. Maybe this is due to the dispersion of light. In general, when white light means it is a composition of several colors, so all colors are combined as white light. So when white light is incident on glass prism, it particularly disperses the light into different colors like this. So whenever we take any solid sample, as said earlier, or any liquid in a cuvette or powder sample, we incident electromagnetic radiation and we observe the light reflected or refracted or transmitted through glass medium or liquid sample. So we observe these light interacted through these materials, and by studying the emitted light, we can observe many phenomena after interaction of electromagnetic radiation with matter. So in order to understand interaction, this type of interaction between electromagnetic radiation and matter, we must know full idea of electromagnetic radiation and matter individually. So first of all, we must discuss electromagnetic radiation. It is having huge range and it can be divided into several ranges such as gamma ray, X-ray, ultraviolet, infrared, microwave, and radio waves. in general, visible light, whatever the light we are able to see, that is having very small region, maybe from 400 to in general 380 to 780 nanometer, very small range among all electromagnetic radiations. And in order to discuss these electromagnetic radiation, we must use terms like wavelength, frequency, wave number, energy. Any of these terms can be used for the description of electromagnetic radiation. So here the wavelength for gamma rays is very small, very small for the gamma rays, and as for X-rays the wavelength increases as we go in this direction. The wavelength increases. So for radio waves, the wavelength is very large. So wavelength can be measured in nanometers for microparticles, as in gamma rays and X-rays, and we can also indicate frequency to describe any wave, and wave number in centimeter inverse, and energy also, energy maybe in joule second or electron volt. So in general, energy can be given by E equal to h nu or hsc by lambda. So if you know frequency of radiation, we can find energy of radiation, and otherwise if you know the wavelength of electromagnetic radiation, by substituting the velocity of light and wavelength and Planck's constant, we can easily find the energy of the radiation. Here h is the Planck's constant, and it is also given as 6.625 into 10 power minus 34 joule second. So the wavelengths are given like this. For gamma rays, the wavelength is less than 0.1 nanometer, and for the X-rays, the wavelength is ranging from 0.01 to 10 nanometers. For ultraviolet, it ranges from 10 nanometer to 400 nanometer, 400 or 380 nanometer. The visible light ranges from 380 to 780 nanometer for visible light, and for infrared, the wavelength is from 780 nanometer to 1 millimeter, and for microwaves, it ranges from 1 millimeter to 1 centimeter, and for radio waves, the wavelength is from 1 centimeter to maybe up to 10 kilometers. So these are the wavelength ranges for different ranges of electromagnetic radiation. So these ranges can be given like this also in terms of wavelength, and again here frequencies are also given for these ranges. And interaction between electromagnetic radiation and matter can be given in three different ways, such as absorption, emission, and scattering. We must know about matter also. Before discussing about these three phenomena, we must know about the matter. Matter means it must be having mass. Material, particle, or matter must having certain mass, and it must have certain position, and it can be described by velocity. Any moving particle can be described by velocity, kinetic energy, and potential energy, and momentum. These are all the parameters to describe any particle moving in the space. In case of wave, in order to describe wave, we must use the terms like wavelength and frequency, time period, amplitude, energy, momentum. These are the terms to describe about wave. There is certain differences between wave and matter, but recent advances according to quantum mechanics says light electromagnetic radiation particularly is having both particle and wave nature. So sometimes it behaves like wave, sometimes it behaves like particle. Particularly phenomenon like interference, diffraction, polarization describes the wave nature of electromagnetic radiation, but later the advances like photoelectric effect and Compton effect describes the particle nature of light. Thus, it can be said that electromagnetic radiation sometimes behaves as particle and sometimes behaves as wave. So it is having both natures. That's why it is said to be having dual nature. So in order to describe the interaction of electromagnetic radiation with matter, these three types of phenomena can occur. So whenever electromagnetic radiation interacts with matter, this electromagnetic radiation may be observed, or some part of light may be observed and the remaining part may be emitted, or this some part of the electromagnetic radiation may be scattered. So depending on the property of matter or substance, these phenomena can occur. So if the electromagnetic radiation is highly energetic, such as UV and X-rays, these electromagnetic radiation can cause for electron to be ejected from the atom or molecular, particularly outer electrons in the atom. So if there is any atom, it can be constituted of central nucleus, and there may be several electrons moving around, revolving around the nucleus in different orbits. Maybe 2 electrons in the first orbit, or 4 or 5 electrons in the second orbit. So in this way, according to the electronic configuration, electrons are arranged in different orbits. So whenever light is incident on this particular atom, this energy, light or electromagnetic radiation of the particular frequency or energy can be absorbed by electron, so that this electron can jump to the next orbit. So energy of the atom changes. So that in general there is a ground energy level for any atom. So when there is a frequency or energy of electromagnetic radiation of sufficient energy incident on this particular energy atom, which is in the ground energy level, so this atom can absorb the energy of light and goes to the higher energy level E2. So if there are two energy levels, E1 and E2 for particular atom, the atom, after observing the electromagnetic radiation of sufficient energy, it goes to the higher energy level E2. This type of phenomena is called absorption. So this phenomena occurs due to the absorption of electromagnetic radiation. This is one type of interaction phenomena of electromagnetic radiation with matter. Sometimes, if there are several energy levels, if an electromagnetic radiation of some certain frequency is sufficient to jump from E1 to some E5, so that the atom in the ground energy level can absorb the energy of electromagnetic radiation, such electromagnetic radiation, and goes to energy level E5. And this atom in the energy level E5 can comes to ground energy level, or directly, or E5 to E4, or E5 to E3, or E5 to E2. So it depends on this type of transitions, particularly depends on the probability of electronic transitions from one energy level to another energy levels. So all these things we will discuss in the next coming lectures. So particularly Such a high energetic radiation of UV and X-ray can cause electron to eject from atom or molecules. So again, the radiation such as infrared region, in the infrared region can cause the electron to vibrate molecules or atoms. So whenever light from electromagnetic radiation is incident on atom or molecule, it can cause for vibration of molecules. So if there is any vibration of molecules observed from the phenomena, we can say that there is an incident or change of energy levels due to the infrared light. So particularly, and again, microwave radiation, it causes for the molecules to rotate. It is less energetic and it cannot cause for any electron to change its position, and it just able to rotate the molecules. So in this way, we described all the phenomena here. Gamma rays particularly causes for the change, that energy changes involve the rearrangement of nuclear particles. These are the wavelengths. That means the wavelength is less than 0.001 nanometer for gamma rays, and this particular value indicates the frequency of the gamma rays. So on X-rays, energy changes involving inner electrons of the atom. For UV and visible light, there is a change of valence electrons, changes involving the valence electrons, outermost electrons in the outermost orbitals of the atom. But in the case of X-rays, it can cause for the change in the inner electrons of the atom, because it is having highly energetic radiation. And if we come to the infrared radiation, it can cause for vibration of atoms, maybe stretching modes can be observed. So compositional change may be in terms of vibration. So it may be observed in vibrational spectroscopy. Vibrational spectroscopy techniques uses the infrared radiation. And microwave radiation, it causes for the rotations of molecules. So rotational spectroscopy is uses the microwave radiation. Radio wave particularly is used in the nuclear magnetic resonance spectroscopy and electron spin resonance spectroscopy. Okay, so all these techniques are highly ingeniously designed to develop or evolve the chemical changes or compound to find out the compounds in different fields of technology. So these are the various spectroscopic techniques, not only limited to these mentioned techniques. There are still several spectroscopic techniques. Here these are the commonly used spectroscopic techniques everywhere, such as UV visible spectroscopy, FTR spectroscopy to find the compounds in the chemical substances, Raman spectroscopy, particularly it is indented to rotational spectroscopy. It is particularly rotational spectroscopy and electron spin resonance spectroscopy, fluorescence spectroscopy, mass spectroscopy, X-ray diffraction, neutron scattering, electron microscopy, NMR spectroscopy, circular dichroism. Still, there are several spectroscopy techniques such as laser spectroscopic techniques, ultra-fast laser spectroscopic techniques, and again there are still several spectroscopic techniques coming in the future generations. So these are the applications. Spectroscopic techniques become the essential tools in the fields such as environmental monitoring, pharmaceutical analysis, material science, molecular dynamics such as time-dependent process and chemical reactions, biological processes, medical diagnostics, astronomy, satellite remote sensing, generation of ultra fast and ultra intense laser radiation, laser cooling and trapping, Bose-Einstein condensation. These are the different fields having the scope of spectroscopic techniques. So these are the references given to study the atomic and molecular spectroscopy. In the coming lectures, we discuss the basic fundamentals behind the atomic and molecular spectroscopy and different techniques used for the development of spectroscopic techniques. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.